This lecture is going to be in chapter 8 from our textbook. And what we start looking at, something called a confidence interval. So as our numbers and our sample size continue to grow, we talked about in the last chapter that they form more of a normal distribution. And we remember these are all estimates, right? When we do these, they're estimates. Now, what we're looking at now is we're talking about a confidence level we're going to talk about of the mean following, or an average falling in between two values. Okay, and we talk about some definitions here, but before I just get into it, let me just kind of define what we're really looking at. And we're really looking at something called a confidence interval. A confidence interval is just another type of estimate, but instead of just being one number, we use an interval of numbers, and it provides a range that we will follow between. There's no guarantee that it will capture what we're looking for, but it is it's predictable and it has quite success depending on what we have. So what we're going to look at, and I'll just go ahead and say, hey, we're in chapter 8. So chapter 8 is confidence intervals. So let's go ahead and just write that. So we're confidence intervals. I guess I can write chapter 8 in here. And in chapter 8, we'll start with section 1. So we're chapter 8. So this is 8.1. And it's called a single population mean using the normal distribution. All right, so first off, we create what we call a confidence interval. In order to create a confidence interval, we are constructing an interval for a known population, so a population mean, where the standard deviation is also known. And we have something called the margin of error, or we'll call it it's called the error bound for the population mean. And that is, we'll see EBM. What's that abbreviation means is we call it the margin of error. Or if you want the full kind of where it comes from, it's called the error bound for a population mean. And then our sample mean, which is X bar, that's called our point estimate. So we're trying to look for the confidence interval. A confidence interval, I'll write this down, confidence interval. It looks something like this. In words, it's the point estimate minus the error bound point estimate. Or I should say the error bound, sorry, error bound, comma, the point estimate plus the error bound. Or using our abbreviations, it looks more like this. X bar minus the EBM, X bar plus the EBM. And I could put up here too is that our confidence interval, we like to use the abbreviation CL. You'll see in the textbook they use it as well. So I should say not confidence interval, I'm at confidence level. So we'll say confidence level, sorry, CL. Another definition that we'll use, because we talk about our confidence level, and we'll say it's we have a 90% confidence level. We'll use 95% very frequently, and I'll get into that more and talk to you about that as well. This textbook uses a 90% confidence level, and really what that's really saying is that there is a 90% chance that it's going to fall in between this this interval. Sorry, I can't think of the word interval. All right, so let's do a problem. I think the best is to do this small little problem. Actually, the textbook does it, and so we're going to talk about it, and then I'll show you. One thing you need to know is that mathematically, what we have is we have another probability. So we have a confidence level, we have another probability, and we call that alpha. All right, you'll see that in my diagram that we're going to get to. So let's suppose we have a collected data, and we know the sample mean, but we don't know the mean for the entire population. So we can call this example 1. So we know the mean is 7. I'll just write this out. We'll know, I guess you write the same color here. We'll say the mean. That should be more clear. The sample mean. Sample mean is 7. And then the error bound for the mean is 2.5. Okay, so let's say this is what we know right now. What does that mean? I probably shouldn't wrote EBM. I should have just wrote the actual thing. So X bar is 7, and we know that EBM is 2.5. So based off our confidence interval that we have right here, okay, we're going to say that our confidence level, our interval, sorry, I don't know why I keep saying level. Our confidence interval is 7 minus 2.5 to 7 plus 2.5. It's going to give us a range. So once we calculate this, this gives us 4.5 to 9.5. This here tells us that we would say that our population mean is between these two values. Now, there's going to be more to these problems, and we'll talk about our confidence level. And so we'll state certain percentages. 90% is used quite frequently here. But let's say we say 95% confident or 90%. So if we said 90%, we would say we estimate with 90% confidence that the true value of the population mean is between 4.5 and 9.5. Remember, this is a range. That means that our population mean is somewhere between these two values. So let's just take some random numbers here and let's run through this. So this is what the textbook uses. So I'm just going to use it to stay consistent. But I'm going to go to another page here. And what you're going to see is this. Let's suppose a few things. This is not quite an example. We're just going to talk through some things. Maybe you call it what you want. But let's suppose that our sample mean is 10, and then our error bound, the mean, is 5. Okay, and we're going to say that we have a 90% confidence level, and I'll explain more. You'll see what that means a little bit better. Remember, that's our CL. So if our probability, sorry, not our probability, our sample mean is 10, and our error bound of the mean is 5, with a 90% confidence level, then our confidence interval, we would say, is 10 minus 5 and 10 plus 5, which would give us between 5 and 15. What this means is that we are 90% confident that our population mean would fall between 5 and 15. Now, graphically, here's what it looks like. Let's draw our bell curve here. We know that our sample mean is 10. And then we have this 5 here, and we have 15 here. What we're basically saying is that this population mean will lie between here, between these two values, and we are 90% confident. So our confidence level is 90%. Here, our sample mean is 10. Our error bound for the mean, we already said, was 5. And I should have made some of these equal signs instead of to be correct here. And then we know that we have x bar minus our error bound is going to give us 5, and then x bar plus our error bound is 15. So one thing I want to talk about, we're on 90% confident that it's in here. So this is 90% probability it's in here. Okay, that's great. But if that's 90%, then what are these two tails? Well, if this from here to here is 90%, that means we have left is all we have left is 10%. But because it's equally distributed on both sides of our normal distribution, that means that here we have from here over, we have 5%. And then from here over, we also have 5%. Okay, we like to call these alpha when we add these together. So what we have is, what I was going to show you a little while earlier, is that your confidence level plus your alpha should equal 1. In this case, our confidence level is 90. I'll put 0.90. Our alpha is the total of these two together. So 5% and 5%, which is 10%. So we'll say 0.10, which is equivalent to 1, because there's a 100% chance of this occurring. Now, what we use is our confidence level, which is 90%. We have to figure out with our z-score what value we're looking for. So how many standard deviations away from the mean are we going to go? So in order to figure that out, is you have to say that, well, hey, 90%, if I take half of that, because this is all 90. If I take half, that's 45. So you have to go to your z table and find the closest to 0.4500. When we use our table, we lie between two values. If I remember right, it's 0.4495 and 0.4505. So when we do that, use our table, we have to start rounding more. But this textbook doesn't use a rounded answer. It uses more of an exact from a calculator approach. So that's what we're going to use. So what we need to know is that when we have a 90% confidence level, when we're at 90%, our confidence level, I'll do this. I can spell it out, I guess. Confidence levels. We are at 90%. Our z-score is going to be 1.645. This is what's going to be consistent with what the textbook uses. And it'll vary if you look at a different textbook. There's been other textbooks that I've used, and 90% is rounded to 1.65. For us, we're going to use a 1.645. Another common one that we're going to use is we're going to use a 95%. 95% is a 1.96. Remember, these are coming from your z-scores. These are how many standard deviations away from the mean over you're going to have to fill out that percentage. And the last one we like to use is 99%. We're going to use a 2.58. So I'm going to give you some steps on how to calculate the confidence interval. I'm going to move to, I have room here. So how to calculate So it's a 5-step process. So step one, you're gonna basically calculate the sample mean, which most everything we have, you're gonna know the sample mean, but if you're not given it, so if you're given just a table of values, you have to find the average. Step two, we're gonna find the z-score. That corresponds to the confidence level. Remember, that's what these are right here. These are z-scores right here. So for 90% confidence, and we have 1.645 as a z-score. 95% gives us a 1.96 z-score, and the 99% gives us a 2.58 z-score. Step three, we're going to calculate the error bound of the mean. Step four, we're going to construct the confidence interval. And last one is we are going to write a sentence. Okay, and I'll try to give you more of like a cookie cutter sentence as well. So let's kind of break down exactly how you do some of these things. So the first step is calculate the average, or sorry, the sample mean. And usually it's going to be given to you. If not, you can just take the values, add them together, divide by the total number of values, right? So that's something that we're used to doing from previous material. Now, finding the z-score that corresponds to the confidence level is a little different. So if I was to go back to our confidence level here, okay, and we look and we see that our confidence level is 90%. I know I gave you these here, but I thought I would just show you what they represent. If this is 90%, remember this means alpha, these two together, which means that these two by themselves are alpha over 2. Because if I add the two together, I get just alpha, right? So what I'm looking at is I'm actually looking at the z-score sub alpha over 2 when I look at these z-scores, because I'm only talking about half of this distribution. So when I look at my z-scores that you have on this next table right below, I'm looking at that only satisfies this right here. And then, of course, this is double, so that's where I get my 90% as accurate as possible. So when I look to find my z-score, really, I guess I could write right here, your z-score is really, your z is alpha over 2. That's what it represents. So alpha over 2, if we're talking about 90% confidence interval, would be our 1.645. Our z sub alpha over 2, if we're talking about 95% confidence level, would be 1.96. Our z sub, or our c score sub alpha over 2 of a 99% confidence interval would be just 2.58. Now our calculating the error bound, the EBM, the error bound of the mean, I'm going to write it this way. So our error bound of the mean can be written as our z sub alpha over 2 times our standard deviation divided by the square root of n, right? Because we're using our normal distribution and we're using the central limit theorem that states as this is what our standard deviation is as our population, our sample gets larger and larger and larger. So we're talking about a mean, we're talking about the average. Now constructing the confidence interval, I'll write it maybe a different color here. We already kind of talked about it. It's x bar minus our error bound of the mean, and then x bar plus our error bound of the mean. So let's go ahead and let's put a visual to this. Let me see if I can put a visual here. So if I was to give you a big visual of what it all looks like, let me try to see if I can squeeze in here and still fit all my lettering that I want to. So first off is we have our x bar. That's our average here. Down here, we're going to have x bar minus the error bound of the mean. Over here, we're going to have x bar plus the error bound of the mean. And this is what we're looking for all in here. This back in here, right there, is our alpha over 2. Same as here, alpha over 2. And then our confidence level is just going to be our confidence level is 1 minus our alpha. So if alpha over 2 was, say, 5%, that means that my alpha is 10%. So my confidence level is 1 minus 10%, which will give us our 90% confidence level. So with all of this, now we still need to interpret. How do we interpret? So here's a good way of interpreting. So this is kind of where it needs to go. So you could say something like this, almost a cookie cutter, exactly like this. We estimate with a certain percentage, so 90, 95%, 99% confidence level that the true population, and then from there, then you will include what the population is, right? So you would say exactly what the population is in there, depending on what the context is. So you put whatever is between blank and blank, which you would get from your confidence interval, and then include the units. So if it's centimeters, meters, feet, time, seconds, whatever it might be. All right, so now, having said that, let's move to our first example. So I'm going to pause this and write it. When you come back, it'll be written here. All right, so here is our second example here. So it says, suppose scores on an exam in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives a sample mean, the sample mean score of 68. Find a confidence interval estimate for the population mean exam score, which is the mean score of all exams. Find a 90% confidence interval for the true or the population mean of statistics exam scores. Let's just go through our steps. So, step 1. We need to find the sample mean. Well, sample mean is in there. In fact, what we should do is go through all of these. What do all these things mean? So we have right here, the sample mean is, where is that? There. This is our X bar. Might as well go through the rest of this. 36 is our sample size, so this is our N. Our standard deviation doesn't have a written number, it's words here. So 3, this is our standard deviation. And last thing is our confidence level right here. Our CL is 0.90. So these are all things that we will use. So step 1, what's the sample mean? The sample mean, we identified it right here at 68. So X bar is 68. Check. Step 1 done. Okay, step 2 says find the z-score. Move up just a little bit. So step 2, find the z-score. Well, if our confidence level, maybe I should write this in a different color here so you can know this is just the thought process. Our confidence level is 90%, which means that if we wrote it in the previous one, our confidence level is 1 minus alpha. And so if this is 90%, oops. Then that means that alpha is 0.10%. We see that our alpha over 2 is 0.05. The main thing that we have to take away from this is that this right here, or z sub alpha over 2, which is z at 0.05, is going to give us 1.645. And that's what I gave to you in the previous one we started going over the steps. All right, step 3. We are finding the EBM, the error bound of the mean. So the EBM they gave us a formula for this, right? So, oops, EBM is our z of alpha over 2 times our standard deviation of our sample. So standard deviation divided by the square root of n, which in our case, our z is 1.645. Our standard deviation was 3, sample size was 36, right? We said 3 here, and then 36. You put this into your handy dandy calculator and you get 0.8225. This is now your error bound of your mean. Step 4 says construct the confidence interval. Well, how do we do that? We really do it by exactly using the formula that we have, right? And it said it is x bar minus the error bound of the mean. Keep writing, get dyslexic here, error bound of the mean, x bar plus the error bound of the mean, which is our x bar is 68. Our error bound of the mean is a 0.8225. So it's 68 plus 0.8225. When we simplify that, that gives us 67.1775 and 68.8225. This is our confidence interval. Now, what do you say here? Step 5, write the interpretation. So we estimate with our confidence level, which is 90%, with 90% confidence, that the true population, the true population mean exam score for all statistics students is between 67.18 and 68.82. Oops, I don't need a period here. This is how you interpret it. Again, what changes in this interpretation? 90%, right? Because it fits your problem. And then this talks about your context. What are we talking about? We're talking about exam scores for all statistics students. And is between, here's your lower bound, upper bound. So how could this problem really change? Let's say we kept everything the same except for we changed our confidence level. Okay, let's say we change our confidence level to be a 95% confidence level. So all of our steps are exactly the same. Okay, we find the sample mean. We find the z-score. I should have put z-score here. I guess I omitted that part, so I apologize there. This should be find the z-score. We find the z-score. After find the z-score, find the error bound and the mean. Then you construct the confidence interval, still interpret. Where is this really going to change? It's going to change right here because that 90% now is going to be 95%, which when I get done with this, that number will affect the error bound and the mean, which then will affect our confidence interval, right? As you can see right there. So it doesn't affect step one. That doesn't change. But as soon as we start changing our confidence level, then that changes drastically our interval in the end. And I'll explain why too. We'll compare the two. So let's just say, I mean, I guess you could say example 3 or whatever you want to say, but we're just going to just say, well, how about a 95% confidence level? So we're going to say 95%. So step 1, you find X bar. We already given it. We were given the X bar is 68. Step 2, find the z-score. Right, which is completely different now because now our z-score, our confidence level is 95%. So if we have a confidence level of 95%, then what that changes now is our z, I'll just do it this way. Our z sub alpha over 2 is now not the, what was it before? It was 1.645 because we're at 90%. Now our 95% gives us a z-score of 1.96. Okay, so that affects everything now because step 3 is find the EBM, the error bound of the mean. Remember how we find that? We find that by saying the error bound of the mean is our z sub alpha over 2 times standard deviation divided by the square root of n is 1.96 times 3 divided by, it was, I believe, 36. So the square root of 36. We put this into the calculator, right? Just like we have it. And this gives us 0.98. All right, step 4. Step 4 is where we say construct the confidence interval. Remember that is X bar minus the EBM, X bar plus the EBM. So in our case, it is, what was our X bar was 68. So it's 68 minus 0.98, comma 68 plus 0.98. We put that into the calculator. We could use a calculator for this. This gives us 67.02. And we have 68.98. That's our confidence interval. Step 5, interpret. How we interpret, we will say the exact same thing, okay, except for what's really going to change because our context is the same, but what changed was our confidence level and our interval. So we're going to say we estimate with 95% confidence that the true population mean for all statistics exams is between 67.02 and 68.98. You can see the interpretation is the same, but again, what changes? Confidence and interval. Now let's talk about what happens when we change the confidence level. Well, when we said 90% in the previous example, our 90% confidence level gave us 67.18 and 68.82. We change it to 95% confidence, meaning that we are more confident. We have 67.02 and 68.98. So what happens? If you just look at these alone, you could say, as our confidence level increases, our interval also increases. Right? So if I had to draw this, these numbers are in between these numbers. These are further. Our bound is larger. So because our confidence level is getting bigger, that means we're going to widen our interval, knowing that, hey, as we widen the interval more and more and more and more and more, then we know that we will fall in that interval. We have more confidence. So increasing the confidence level increases the error bound, making the confidence level wider. Decreasing the confidence level decreases the error bound, making the confidence interval more narrow. So let's just keep going with this. What happens if we just mess around with the sample size? Okay, we don't need to mess with anything else, but let's just say sample size alone. So we have the same exact problem. But now let's say that we have a 90%. Let's go back to our original 90% confidence level interval. And now we're going to say, instead of 36, let's say 25. And instead of 36, let's say 100. Let's just use nice numbers because then we don't really necessarily need a calculator really big for this, because square root of 25 is a lot easier. It's easy to find. Square root of 100 is also easy to find. So let's say we tweak the sample size. So what happens? Well, let's see what directly affects. Our X bar is the same. X bar is still 68. When we find our error bound of the mean, again, there was my dyslexia. Error bound of the mean, alpha over 2 times standard deviation divided by the square root of n. Our confidence level is 90. We're going to keep that the same, which means that our z-score is still 1.645 from our previous, right? Because that's what we needed. So when we change the sample size, what gets affected here? Doesn't our error bound the mean get changed? When this gets changed, doesn't that affect our interval? So let's say n is large. Let's say 100. If n is 100, that means that the error bound of the mean is z sub alpha over 2 standard deviation divided by square root of n. We say 1.645 times 3 divided by the square root of 100. That's going to give us 0.4935. That is our error bound of the mean. Let's look at what happens when we decrease that to 25. Our error bound of the mean, z sub alpha over 2, standard deviation divided by the square root of n, 1.645, 3 divided by now the square root of 25. This is going to give us 0.987. We could even go back and say, well, what was it when we had 36? No, you could say 25 is close to it, but we can say, so when n was 36 is what we did in our first original problem. All right, error bound of our mean. I'm not going to write it all out. I'm just going to write what we got was 0.8225. And actually, I could do this. Show you something. Let's put them in order here. As my sample size gets larger, what happens to my error bound of the mean? It gets smaller. Or you could say as my sample size gets smaller, my error bound of the mean gets larger. Why is that? Well, I'm directly dividing by a smaller value as we keep getting smaller values. Here I'm dividing really by 10. Here I'm dividing by 5. All right, so here's what you can say here. When you increase the sample size, it causes the error bound to decrease, making the confidence level or interval more narrow. If I decrease the sample size, it causes the error bound to increase. So decreasing causes this to be large, making the confidence interval much wider. Because we don't have as many samples. So we're pulling from a smaller sample size, therefore we have to get out further to make sure we're more confident that the population mean falls in that interval. Okay, so we're going to move on to one more thing, and then, well, actually, it's really two more things, and we're going to call it good for this section. So first is, what if we need to find the error bound? What if we don't know what the EBM is? There are really two ways of doing this. Okay, one is from the upper value for the interval. Let's see, from the upper value for the interval, you can subtract the sample mean. Or from the upper value of the interval, you can subtract the lower mean. Then divide the two. Oops. Divide the difference of the two. All right, so let's just get right into that example. Let's call this example, well, I guess I get the same color code here. This is example 3, if I remember right, officially. So let's say we know the confidence interval is 67.18 to 68.82. And we want to find the error bound of the mean. That's what we don't know. Let's say we also know that the sample mean is 68. All right. So let's say we know this. So let's say, hey, X bar is 68. We'll keep using the 68 thing. So let's calculate the error bound. So let's use our first thing. So let's say we know the sample mean, like I just said. We know X bar is 68. If we know that, that makes it really simple. That means that the error bound of the mean is the upper bound, which is 68.82 minus 68. So that means our error bound of the mean is 0.82. Perfect. How about we don't know the sample mean? All right, that was the second thing. We don't know X bar. So what we do, take the error bound of the mean. How do we find this? We add the two upper bound, well, the lower and the upper bounds together. And then we're going to divide by 2. So we're going to subtract here. Sorry, add them together. And then we're going to divide by 2. I'm sorry, I was right the first time. I kept wanting to go back and forth. What we need to do is I need to go back here. From the upper value, subtract the lower mean, then divide the 2. My fault. Let's try and get ahead of myself here. So it's 68.82 minus 67.18. Divide by 2. This gives us 0.82. I apologize. Okay. Now what happens when we don't know the sample mean? What if we don't know, what if we want to calculate the sample mean? We don't know it, but we say, hey, you know what? We should know this. We should know what the sample mean is. So we'll go back to another color here. And we're going to say, find the sample mean. So first, subtract the error bound from the upper value. Of the confidence interval. Or second, average, this is what I was trying to do prior, and that was my fault. Average the upper and lower endpoints of the confidence interval. So let's plan like we're using the exact same thing up here. We know the confidence interval is the 67.18 and 68.82. Okay. We now know the error bound of the mean, but we want to calculate the sample mean. Let's say we don't know this at all. So the first case scenario is we know this. That's the easy one. So So we're finding X bar here. So first one is we know the error bound of the mean. So to us, that just tells us that X bar is 68.82 because it says subtract the error bound from the upper value. Our upper value is 68.82. Our error bound of the mean was 0.82. So that means that our mean is 68. Done. Let's say we don't know the error bound of the mean. So now here we average the upper and lower endpoints of the confidence interval. How you average? You add them together, divide by 2. So that means X bar is our lower 67.18 plus our upper, which is 68.82, divided by 2, which gives us 68. Same answer, different roots. All right, one more thing before we end this section. Last thing is how to calculate or find the sample size. How do we calculate the sample size? So there is a formula that has been developed to find the sample size, but there's some things that you need, right? So I'm just going to give this formula to you, and then we're going to talk about what you need here. So it is n equals the z-score squared, standard deviation squared, divided by the error bound of the mean squared. Where does this formula come from? It comes from right here. If the error bound of the mean is z sub alpha over 2 times standard deviation divided by the square root of n, this is exactly how we find and manipulate. If we're solving for n, we manipulate it to get here. Okay. Now in this case, this z sub alpha over 2 is just say we're talking about z here. So let's talk about something. If we have to have all these things, we don't have to really do a problem here because we have to have 3 of these variables to find the 4th one. So what do we need? We need the z-score, we need the standard deviation, and we need the error bound of the mean. Now, how do you find the z-score? Remember, if it says it's a 90% confidence level interval, at 90%, you're going to have 1.645. At 95%, you're going to have 1.96. At 99, you're going to have 2.58. In fact, let's just do a problem because I want to make sure I show you something. So let's say that the standard deviation, we'll call this an example, I guess. The example 4, I recall. What we have is we say the standard deviation, I'm just going to give you some things, is 15. So we want a 95% confidence level. Okay, and we're going to say that the error bound of the mean is 2. So when we're looking at this formula, we have standard deviation, check right there. Error bound of the mean, check right there. But we don't have the z-score. We have to use it from right there, the confidence level. So remember that our 95% confidence level gives us a z-score to be 1.96. Now we can calculate our sample size. N is 1.96 squared Our standard deviation is 15 squared. Error bound the mean is 2 squared. When we substitute this into the calculator, it's 216.09. Now, the one thing you have to remember is the context. Let's say this context was talking about a number of books. Well, number of books, there's no such thing as 0.09 of a book unless you literally cut it, right? And slice and dice it. So anytime we're trying to look at a sample size, we're always going to round up in order for it to make sense, right? Because we're talking about individual things. So this case, our N is going to be 217, whatever the units are. We're always going to round up here with our sample size. We want to make sure our sample size is large enough. That is the purpose. If we cut it short, then the whole thing is going to be cut short. We want to make sure that it is at least large enough.